Today we will cover Chapter 10, Liquids and Solids. So here we cover intramolecular forces and intermolecular forces. Intramolecular forces are forces within molecules, and they are stronger. They determine chemical properties of molecules. Intermolecular forces are between one molecule and another molecule. They are weak, and they determine physical properties. We'll cover these physical properties later. Some types of intermolecular forces include London dispersion forces, dipole-dipole attraction, hydrogen bonding, and ion dipole forces. As you can see, ion dipole forces are the strongest, hydrogen bonding is the second strongest, and London dispersion forces are the weakest. London dispersion forces occur between all species and results from the uneven distribution of electrons, or a dipole moment. It depends on the size of the molecule. As molecules get larger, they experience more London dispersion forces. As molecular shapes becomes more elongated, it becomes more polarizable and experiences more London dispersion forces. Dipole-dipole attraction occurs in polar molecules which have permanent dipoles. It occurs between a positively charged molecule and a negatively charged molecule where the different dipoles attract. To determine polarity, you can see that something is polar when the atoms are asymmetrically attached, or if there's a one lone pair and the lone pairs are asymmetrically attached to the central atom. In a non-polar molecules, the lone pairs can be symmetrically attached around the central atom like this, or they can be in symmetrical geometries. In hydrogen bonding, we see that it must have a hydrogen attached to a fluorine, oxygen, or nitrogen, or I like to remember it as phone. Here we can see where hydrogen is attached to FON, and it is then attached to another FON on another molecule, which can be attached to anything else. Ion dipole forces are ionic compounds plus polar molecules. Ions are attracted to the dipole of the polar molecule. For instance, cations are attracted to the negatively charged side of this molecule. Higher the charge on an ion, the stronger the attraction, which makes sense because they are more polar and they would attract. Smaller the size of the ion, the stronger the ion dipole attraction. Again, with a smaller size, as we saw here, a smaller size means that they are better for dipole attraction. Properties of liquids include viscosity, which is the measure of the resistance of flow. As the intermolecular forces increases, meaning the molecules become more closely bonded to each other, we see that viscosity increases, making it thicker things. An example of something with a high viscosity is honey. Something with a low viscosity might be water compared to honey. As temperature increases, viscosity decreases. So if you heat up honey, it flows faster, meaning viscosity decreases. And the larger and more complicated the molecules, the higher the viscosity. Surface tension is the tendency of liquids to minimize their surface area. As intermolecular forces increase, surface tension increases. This is because surface tension occurs when one molecule is attracted to its surrounding molecules. And this is how intermolecular forces work when a molecule is attracted to other molecules around it. As the temperature increases, surface tension decreases. An example of thinking about this is when you go outside and dew, when the sun comes on, dew that is on grass melts, meaning the surface tension isn't holding anymore in high temperatures. Capillary action is the rise of a liquid on a narrow tube immersed in liquid. This is due to the attraction of a liquid to the surface area of the tube. As you go from solids, they have the highest density and the highest intermolecular forces. Gases have the lowest density and the lowest intermolecular forces. Vaporization refers to liquids becoming gas. It is an endothermic process because you need heat to make liquid to gas. And energy is required to overcome the intermolecular forces, to go from a high density to a lower density. And so, because it's endothermic, the enthalpy is positive. This opposite is true for condensation. It is basically gas going to liquid. It is an exothermic process that releases heat. and energy is released, and therefore enthalpy is negative. Rate of vaporization. As temperature increases, the kinetic energy increases to overcome intermolecular forces, so the rate of vaporization increases. As the surface area increases, molecules are held less tightly, and therefore the rate of vaporization increases. As the intermolecular forces decrease, the rate of vaporization decreases. Vapor pressure. That is the amount. Okay, here we can see that the enthalpy of sublimation is greater than the enthalpy of vaporization and of fusion. We know this because this is going from solid to gas, and it might require more heat to break up those intermolecular forces, and therefore might be harder. The same can be true for the other phases. Okay, phase diagrams are diagrams that map out temperature, the x value, versus pressure, the y value, to have a graph. Here we can see that there's a triple point where three different curves meet up. Here we can see the sublimation curve, which goes from solid to gas. We can see the fusion curve from solid to liquid, and the liquid-gas curve or vaporization curve. The triple point is when all of these three curves meet. It is important to note that these three curves do not have to be the curves here. They can be different ones with different states that might exist. A critical point is the highest temperature and pressure at which pure material exists in a gas or liquid equilibrium. After that, there is a supercritical fluid right here. And here is what a supercritical fluid is. It is when no distinct or liquid or gas phases exist. It is a property, and the supercritical property has properties between a liquid and a gas. It has stronger intermolecular forces and makes a great solvent. And we can see the temperature for the critical point increases with intermolecular forces.